Hi folks! This video on rearrangements is going to cover ones that involve biradicals, molecules containing more than one radical in a single molecule. For today's video, we're going to have to consider what happens to molecules when they're heated to very high temperatures. And a common consequence of this heating is that bonds will start to cleave. Thermolysis refers to thermally induced bond cleavage, so I'm going to use that term a lot throughout this video. For simple molecules that are not cyclic, thermolysis is going to form two separate radicals. So for example, if you heated hydrogen peroxide, a homolytic cleavage of the weakest bond in the molecule would occur. This is the oxygen-oxygen bond. And this would form two hydroxyl radicals. It's also possible for thermolysis to cause cleavage of carbon-carbon bonds. So for example, if you heat ethane to a really high temperature, homolytic cleavage of the carbon-carbon bond can occur. For ethane, this would form two equivalents of methyl radicals. So notice in each of these simple cases, a molecule not containing a ring generated two separate radicals upon thermolysis. If instead a cyclic molecule is heated, a bond could break to form a biradical. This is a single molecule containing two radical centers. So for example, let's consider cyclopentane. At very high temperatures, it's possible for a carbon-carbon bond in this molecule to break. This would occur homolytically. This cleavage causes the ring to open up, but the two carbons containing the radicals are still attached to the same molecule, and we would refer to this as a biradical. First, I want to talk about heating up cyclobutanes to form a special type of biradical called tetramethylene. So imagining starting with cyclobutane, a fairly strained ring. At high enough temperatures, thermolysis will break one of the carbon-carbon bonds of this molecule, and this would form a biradical tetramethylene. Here notice the radicals are separated by two carbons. This ring opening to generate a biradical intermediate can cause cis-trans isomerization of substituents on substituted cyclobutanes. So let's imagine starting with a cis-disubstituted cyclobutane ring. Upon heating, the carbon-carbon bond of the ring with the two carbon substituents on it would break. This is the biradical formation step. And by breaking the carbon-carbon bond with the substituents coming off of it, you get, in this case, a secondary radical. This is more stable than a primary radical would have been. What can happen is some of the carbon-carbon bonds of this ring could rotate in order to give the isomerization. So I'm going to imagine this lower part of the molecule rotating. This could generate a conformation where this bond to the R group is now a dash instead of a wedge. And from here, to reform the cyclobutane ring, you could bring the two unpaired electrons of the biradical together, and coupling of these electrons of this conformation of the biradical would give a trans-disubstituted ring. So here we opened up one of the carbon-carbon bonds of a small ring in order to form a biradical intermediate, and that allowed a bond rotation in order to form a new isomerized product. It's also possible that the tetramethylene biradical intermediate could cleave to give two alkenes. Here the first step of the mechanism would be the same. Upon heating, the carbon-carbon bond would break to generate the biradical intermediate. From here, we won't worry about stereochemistry, but we're going to deconstruct this molecule by breaking this carbon-carbon bond and forming alkenes. So what this would look like is bringing the radical down and one electron over to form an alkene. Then I'll do the same thing on the other side, bring one electron down, and one electron from the carbon-carbon bond over. And the four curved arrows show the two pi bonds forming, and the carbon-carbon single bond breaking. It's also possible to get to tetramethylene, that biradical separated by two carbons, starting out with a cyclic diazine molecule. What this would look like is a six-membered ring starting out. These two nitrogens are known as the diazine. And once N2 is lost, you would get a biradical with an electron here, two carbons separated from another unpaired electron. So what this would look like is breaking the carbon-nitrogen bonds. So I'll start with the one at the top, taking one electron from that bond to carbon to make a radical, one electron over to start to form the nitrogen triple bond. For the other carbon-nitrogen bond, I do the same thing, one electron to carbon, one electron coming down to form the triple bond. And this step would generate the tetramethylene biradical and nitrogen gas. So you can imagine this step would be very entropically favored. One example of a cyclic diazine that has been studied is this one, where you have two chiral centers at the carbons attached to the nitrogens. Upon heating, dinitrogen would be lost, and the following biradical intermediate would be formed. In this case, the original radical sites are each tertiary, so fairly stable compared to other radicals. One possibility is that before any bond rotations could occur, these two unpaired electrons could come together to form a four-membered ring. So notice here, my stereochemistry at these two carbons has remained the same from the starting material. Alternatively, it's possible that a bond rotation could occur, and here I've shown the rotation of the bottom part of the molecule, switching the positions of the ethyl and methyl substituents. If this rotation occurred, these two unpaired electrons could come together at this stage to form the new carbon-carbon bond of the four-membered ring. So notice we have different stereochemistries for these two potential products. What's experimentally observed is that almost all of the product is this one on the left, where bond rotation did not occur prior to carbon-carbon bond formation, and only a little bit of product formed where the rotation had taken place. This implies that the biradical forming a carbon-carbon bond to make a four-membered ring is faster than the bond rotation in this case. It was proposed here that the bond rotation may be slower than usual due to the fact that this is a fairly bulky and substituted substituent, so that rotation may be slowed down by that steric bulk. Now I want to consider three-membered rings and their biradical formation upon thermolysis. Heating up a cyclopropane ring will generate an intermediate where a carbon-carbon bond has broken and you have a biradical, where the two unpaired electrons are separated by only one carbon. This is known as trimethylene. Similar to what we saw for four-membered rings, it's also possible that this heating up of cyclopropanes can cause cis-trans isomerizations if you have multiply substituted cyclopropane rings. Here, let's imagine starting with a cis-disubstituted cyclopropane. Upon heating, this most substituted carbon-carbon bond of the three-membered ring would break homolytically. This would form a biradical intermediate. Initially, the stereochemistry would be the same as the starting material, so I've drawn both of the R substituent bonds as wedges still. If this biradical has a long enough lifetime, one side of the molecule could rotate before the carbon-carbon bond reforms. I'll consider rotating the right side of the molecule, but this could also occur on the left. This rotation about this carbon-carbon bond would change the orientation of the R group on that side of the ring, so I'm drawing that group as dashed now instead. And to form the trans product, I could bring these two unpaired electrons together to form a new bond. Forming this carbon-carbon bond in this conformation would form the trans-disubstituted ring. Another possibility is that the biradical intermediate would form, and then a hydrogen shift could occur. Here I'm not going to worry about the cis-trans stereochemistry. We're just going to imagine starting with a disubstituted cyclopropane and breaking the carbon-carbon bond upon thermolysis. This would form that biradical intermediate. From here, a 1,2 hydrogen shift could occur. So I'm considering the radical position as 1 and the hydrogen being present at the 2 position. This rearrangement is going to generate a new carbon-hydrogen bond, and it's going to generate an alkene. It'll have 4 curved arrows, so 1 from the radical and 1 from the CH bond coming together to form the new carbon-hydrogen bond, and then the other electron from the CH bond going over, and the unpaired electron coming as well, and these 2 curved arrows coming together form the new pi bond. So in this 1,2 shift, the first 2 curved arrows showed the new formation of the carbon-hydrogen bond, and then the second 2 curved arrows formed the alkene. For cyclopropanes, they are very reactive, and it's difficult to predict whether cis-trans isomerization or this 1,2 hydrogen shift would be favored. You'd really have to look at experimental data. A special type of biradical intermediate is known as trimethylene-methane, and this is formed from the following starting material: methylene cyclopropane containing a 3-membered ring with an alkene coming off of it. Heating methylene cyclopropane causes the carbon-carbon bond that is opposite the alkene to break homolytically. And the reason this particular bond breaks is because it generates a resonance-stabilized biradical. So the initial resonance form you would get to upon the bond breaking that I showed would be this one on the left, but there are 2 other possibilities, placing the radicals and pi bonds at different locations. This is the intermediate that's known as trimethylene-methane, or TMM for short. These biradical intermediates can undergo other rearrangements as well as cis-trans isomerizations. So the cis-trans isomerization would be looking at wedges and dashes to the R groups, but the placement of the alkene would remain the same. And the other isomerization gives a pretty different looking product, where the alkene substitution changes upon rearrangement. On the next page, I'll be drawing out the curved arrow mechanisms for the cis-trans isomerization as well as this other rearrangement reaction. The cis-trans isomerization, which I'll start with, is going to look pretty much the same as the ones we've seen for other 3-membered and 4-membered rings. I'll start with a homolytic cleavage to generate that resonance-stabilized biradical intermediate. Initially, when the biradical forms, because the carbon-R bonds were wedges before, they are wedges immediately after this bond breaks. A carbon-carbon bond rotation on either the left or right could change the orientation of the R group. So I'll show a carbon-carbon bond rotation on the right side again. On the left side, the bond to R is still a wedge, but now the bond to R on the right would be a dash instead. These 2 unpaired electrons could recombine, and this coupling would reform the 3-membered ring with the trans geometry of the substituents. For the other rearrangement, the first step is going to be the same, cleaving the carbon-carbon bond homolytically. And to get to the other rearrangement product, we're going to have to consider resonance. So notice that the unpaired electrons are adjacent to a pi bond. I'm going to draw the resonance involving the unpaired electron on the right. To get to the other resonance form, I'm going to bring this unpaired electron down and one electron from the pi bond over to form a new pi bond, and the other electron from the pi bond up to carbon. This would form a new pi bond on the right and place the new unpaired electron at the top of the molecule. The unpaired electron on the left has remained in the same location. To get to the other rearrangement product, I'm now going to reform a carbon-carbon bond between these two radical sites. So I would bring these two electrons together using fishhook arrows, and this reforms the three-membered ring. And notice that this gets to the product where I have the more substituted alkene. Alright, so in this video I talked about rearrangement reactions involving biradical intermediates. These typically formed when a carbon-carbon bond of a small and strained ring broke homolytically due to high temperatures. In this video, I focused on 3- and 4-membered rings, and I talked about several different types of rearrangements that can occur. That's it for this video. I will see you in class.